program. Okay, this is the trick first you use. Okay, because remember, we have to prove that whatever super key is, it determines all these attributes, all the attributes. But if given functional dependencies, if we look at the given functional dependencies and look at all the right-hand sides here, A, B, F, E, this. Now, if something is missing here, doesn't matter what you do, whether you touch your yourself through your legs or otherwise, you cannot get it. So on the right-hand side, nothing can be gotten unless we see here what is not there. B and C are not here. Therefore, B and C can never be gotten. Therefore, they must be put as part of the super key. Nothing without B and C will be part of the super key. Nothing. Look over this problem. R, A, B, C, D, B, C, 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 D, and D, F. See, I wrote it here. Here, what's the problem? Well, on the right-hand side, B is missing. That means any key of this relation must have B. And of course, we can prove AB. When you show AB is a super key, you have to also show that A is not a super key because the closure of A is A, closure of B is B. Okay? But we know B must include here because we try to show whether AC is a key. Well, no, we only got ACD because B cannot be gotten. Okay, here. Now, here is another trick here. All right. So what did we found here? On the right-hand side, B and C are missing. And we said, oh, let's try B and C first. And we tried B and C. And its closure turns out to be first BC. And then we look at on this top here. Well, AB is not a subset of BC. F is not a subset of BC. But C is. Therefore, we stuck DA here. Then we go again. Second iteration. Is AB a subset of BC, DA? Yes, but we already, oh no, we don't have it. So we put F in. Is F a subset of ABCD? No. Is C a subset of this? Yes, but we already have it, DA. So we go next time again. Is AB a subset of BCDF? Yes. Okay, but F is already here. Is F a subset of this? Yes. Therefore, put the right-hand side, which is E. Is C a subset of this? Yes. Put DA, but we have already DA. Now, we have to do one more step, and we will get the same answer. Then we say BC closure is A, B, C, D, E, F. Now, we can also show that the closure of B alone is B and C alone is CDA. So that's it. So that means B itself, or C itself, they cannot be super keys. Therefore, BC is a minimal super key. Therefore, it is a key. But we know something else. Since for any super key, BC must be a part of it, and also BC must be a part of a key because it's a minimal super key. Therefore, what's the conclusion? Okay, a couple of things here. Let's write it down. BC is a key. Okay, we showed by showing. Okay, write it again. BC is a minimal. You have to show minimal super key. And therefore is a key. So what does that mean? Every key must contain BC. If that is the case, and BC is the key, anything else you will get from it is will be what? By adding to BC, what will we get?
A super key.
Super key. So therefore, BC is the only key. You don't have to check anything else. BC is the only key. Okay, now let's, we did some definitions before. Okay, any attribute and attribute part of a key, messed it up. Any attribute that is part of a key is called prime attribute, okay? Oh, by the way, a relation can only have one prime key. Some of you keep on writing 3 prime keys, 4 prime keys, all that. That's not correct. Okay, an attribute that is part of a key is called a prime attribute. Okay, now in this example here, okay, what are the prime attributes in this example? Now let's call this example 1, and this was example 2. So in example 2, what are the prime attributes? What are the prime attributes, guys?
B and C.
That's right. Prime attributes are B, I'll just write down C. Now, what are the non-prime? Non-prime means they are not part of any key. Non-prime. In this example, what are non-prime? Come on, guys. Eric, what are the non-prime? All right, Brett is going to tell me. Brett, what are the non-prime? Anything which is not part of the key. The only key is BC. So what are all the attributes which are not part of the key?
Everything else.
Yeah, what are those?
It's A, D, E, F.
A,
D, E, F.
D, E, F. Thank you, guys. Okay. Now, here, let me see you don't get confused here now. Okay. In this relation, example 1, okay, we know the keys are, let me write it down here. The keys are, we found them, but let me just write it down. They are A, B, everything has to be B part of it. B, C, and B, D. Okay? AB is a key, BC is a key. So you can quickly establish, if you want, by finding the closure of each one of them and then finding the closure of A, B, C, and D separately. Okay? Okay, so in this example 1, what are the prime attributes? What are the prime attributes? Guys, come on. What are the prime attributes? Any attribute which is part of any key is prime. So here, key is A, B, B, C, and B, D. So what are the prime? A,
A, B, C, D.
A, B, C, and
D.
C. This is a very important example. What are the non-primes? Come on, guys.
There are none.
Don't give her, let her control everything. What are the what are the non-primes? Who was talking? What is the non-primes? Come on. What are the non-primes? Everybody.
Attributed.
What?
You talking about definition or the ones in this example?
What do you think is written here? Example 1. I want to know, what are they? What are the...
There
What
aren't
are
any. Everything is prime because it covers everything. A, B, C, D.
It's empty. There is none. Sometimes we write the set like this. Okay? Come on, guys. It's not hard. Okay. Now, this example is going to be so important. You're going to find that this one makes life so easy. Okay. We are going to give one more definition here. All right? So we just said that if we have this example, we saw B and C was the key, and B and C were prime attributes, and everything else was non-prime. Okay? Actually, all these examples are very important because they are going to create a lot of confusion for you. Okay, so what I'm going to do is keep them right here and give you something a little simple, then I'll come back to it because they are very important. Okay, so let's look at R parenthesis A, B, C. This was one of your examples. Okay, and I said here, two functional dependencies, B determines C and B determines. Now we're going to use our head, like what trick I gave you. So we are going to call this example 3, okay? So remember this, guys. Come on. I messed it up. Okay. So I'll call it 3 anyway. Okay. Example 3. Okay. Now, we are going to use that trick we just learned. We want to find its key. Well, look at the right-hand side. What do we see on the right-hand side? Something is missing. What is that?
A and B.
A and B. That means, what does that mean?
That we're going to start with A, B.
We're going to start with A, B. If that doesn't work, nothing is going to work. We will have to add something. Okay? So what's the closure of that? A, B.
Plus
And
A.
then we ask the question, is B a subset of AB?
Yes, it is.
Yes. We get C. Is B a subset of AB? Yes. Then we get D. So we get both. We will get.
A, B, C, D.
Anybody has a question, please, because this is very important and simple. And soon we'll get into a little bit complicated.
Oh, once we're done with this example, I have a quick question.
Just 1 second. Hold it. I'm not done.
Sure.
Okay. So in this, we saw that AB must be part of a super key. But now we want to establish that AB is a key. So what's the closure of A? What's that equal to? It's only A. And what is the closure of B? It's equal to B,
B, C,
C, and
D.
D. So what does that mean? AB is a minimal super key. Since it's a minimal super key, therefore AB is a key. Now, since AB has to be part of every key, Therefore, we can put anything in it because it will only be a super key. It will not be a minimal super. And it is the only key. This is not a key, but it's the only key. Okay. Now, what's by definition? What's prime and what's non-prime? Prime is
A, B is prime. A and B is prime.
A and B are prime. A is prime, B is prime. And what is non-prime?
C and D are non-prime.
Let's use a different color. What is non-prime?
C and D.
I could have write with one word, but I'm just going to leave it. Okay. So non-prime is what? C and
D.
D. Okay. There's one more definition coming. So anything which is part of any key, any prime part of any key, just like here, there are many keys. Anything part of this key, A, B, C, D, all of it, everything is a prime. Nothing is left. And here, two things are prime and one is C and D are left. Okay? I should have a comma here in between because it's not one word. It's comma here. Okay? Now, we need another definition. Okay, it's right here. Okay, here. Oh, I got to rewrite it here. Okay. All right. I'm going to explain something called partial dependence. Okay. What the heck that means? Okay, here. Okay. I'm going to say an attribute, okay? An attribute now, this very important, which I would use a different color. This is a very important. I'm going to use black color first. It's not an, it's going to be a. Non-prime. Just use single word. A non-prime attribute. Okay, guys? Non-prime. Not prime. A non-prime attribute. Okay. We are going to learn in a little while that is the non-prime attributes which creates all the problems. Even in when we have integrity constraints, all those things in the database and everything, it's not the keys create problems. It's the non-prime attributes. Okay? So by definition, a non-prime attribute, okay, is, no, wait a minute now. Just 1 second. Give me 1 second. Just a second. Okay. All right, let me give us an example here. Just a minute. Okay. All right. I was just looking at the handout I gave you guys. So it is in the handout, correct? Okay. All right. So remember, we are talking for non-prime attribute. Is said to be, you don't have to write it, it's in your handout, to be partially dependent. Oh boy. Functionally. On any key, not just on a key. A means in parentheses any key, if and only if it is functionally dependent on only part of some key, part of a key. Okay. Now I got to give you examples here right now. Let me show you. Okay. Now let's look at this. What do we see here? We have non-prime attributes here. What are non-prime attributes? We already found out C and D. Yes? Is everybody with me?
Yes.
Yeah.
C and D is non-prime attributes. Now we want to check whether C or D is only part of a key, only partially dependent on a key. Well, the only key we have is A, B. So either they're dependent on B alone or A alone. I'm going to draw a little picture for you, okay? And sometime you can keep that in your head, okay? Here's the picture. Do we have the color? Yes. Here's the picture. Okay. So in this picture, I'm going to show a key. Okay. And in the key here, I'm going to show two little boxes. One is going to be a tiny box here, and then going to be another box here. Okay, I'm sorry I didn't draw this in your handout. So please write it down, okay? So now I'm going to use red here, okay? All right. In this, I'm going to write B. In this, I'm going to write, what do you think I'm going to write in this? What's the key? AB. And on the top, I'm going to give the heading key. Okay, so what did I do? I drew a box where the prime attributes are in here. Now I'm going to draw a tiny box here and another tiny box here. And I'm going to show in here both the non-prime attributes. What are they?
C and D.
C and D. Oh boy. Okay. Now, what happened here? Okay. Why we don't have a little bigger picture there? What happened? All right. I got to close you guys here. Make a little bigger picture. Okay. All right. Everybody sees it?
Yes.
Now, okay.
Yep.
In the picture, I am going to show that, okay, AB is a key, therefore it determines all attributes. It must determine C and D also. Should it or no?
Yes.
I am going to draw a little arrow here, right here, okay, and here. So what I am saying is AB determines C and AB also determines, come on guys, but we have another fact which is very different, which tells us that B alone determines C and B alone determines
D.
D. So that means these two attributes which are non-prime, they are only dependent on part of a key. So therefore, they are partially functionally dependent on the key. Now, you think you understand this, right? Okay, let me tell you this. A function, a relation is said to be second normal form. It's written there in your handout. If no non-prime is functionally partially dependent on any key. Okay, here, let me write down this quickly. Okay, what color? Black. Okay, so a relation R is in second normal form. If and only if no non-prime attribute is partially dependent on any key. Okay, or any key means a key. Okay, now look guys, I have your exam question right here, and if you can understand this exam question, you will be able to do any quiz and exam. I have right here for you. Okay, so we see example 3. In this picture, we see these are the two primes. These are two non-primes. And they are partially dependent on the key. There's only one key anyway here. Therefore, this relation is not in third normal form. This relation R, example 3, right, is not in third normal form. Is that conclusion okay?
Yes.
Example 3, relation R is not in second normal form. We are going to use this short normal form, okay? Now, here is a question for you guys. What about this example 1? Is that a normal form, second normal form, or no? Well, let's apply the definition. What are the primes here? What are the primes in example 1?
A, B, C, D.
How many non-primes are there?
None. It's empty.
None. So therefore, obviously, this satisfies the case. If there's nothing to, let's say all candidates are got passed, so there's nobody to fail. Okay, whatever. Okay, so there is no non-prime. So the condition is satisfied. Therefore, this relation is in, example 1 is in what?
Second normal form.
Second normal. Okay. Now let's ask another question here, right here. Now this one, if you can answer this question, then means you guys understood it. So this example 1 relation are in second normal form. Let me ask you this question now. This is going to be a little bit hard, and think carefully. Don't try to blurt it out. Let's look at example 2. This example. How many keys it has? It's written right here. How many keys it has?
1.
B and C. What are the prime attributes? B and
C.
C. What are the non-prime attributes?
A, D, E, F.
A, D, E, F. Now, is there any non-prime attribute here dependent on part of a key?
Yes.
Okay?
Yes, it is C.
Okay, because C is a part of key. So by the way, really speaking, according to Armstrong's axioms, when we say C determines D and A, we really mean C determines D and C determines
A.
D. It was just, we can decompose it or we can put it together. So now, that's why it's very important to have, when you answer this question, have single attribute on the right hand side. Please note it down. I think I might not have written down there. Write it down on the top of normal form. When you are checking this normal forms, make sure on the right hand side is a single attribute. Please write it down. Let me write it down because I may not have done this. Left hand side, right hand side. Right hand side must be single attribute. Otherwise, you might get confused. Even your algorithm can get confused. Okay, so what do we see here? Because what? C determines D and C also determines
A.
B. Over here, D is actually a non-prime. Therefore, this relation is not in second normal form. Let me show a picture for this because I think otherwise you might guys have a problem. Can I draw the picture over here in this area? I'll get the red thing here. Can I draw the picture in this area?
Yeah.
Okay.
I'm kind of confused. Doesn't C determines D and A?
Just say it again.
Doesn't C determines D and A instead of B?
Yes, DNA, not
Okay.
B. Oh, sorry. Why did I write B here?
I know, that's what I was thinking.
Okay, it's DNA. That's what I was saying. What happened to my example? This is my special example. Woo! Thank you.
No.
Okay, let me draw the picture. Okay, so that we can do this. So this is B. E. You even threw me off. Some side that I didn't even look at it. Okay, all right. So here is, let's say here is A, okay, and here is D, and here is E, and here is F. Okay, so let me draw this little box here, little box here, little box here. Okay, now we know, okay, oh, this is the key here, so I should write it down. This is the key. Okay, now it's very clear here when we look at this picture. We know, okay, I'm going to draw this. I'm going to, come on, connect this, connect this. Okay, now we did see right here that when we did BC closure, we got everything. Therefore, BC together functionally determines A, it determines D, it determines E, it determines F. Okay, first of all, please notice in the picture here, all the attributes which are part of a key are shown in this big box, and all the non-prime attributes are shown outside the box. Now, if I take this example, I will have to have 1, 2, 3 boxes, each showing a different key. But what will be outside the box? Non-prime attributes. But is there any non-prime attribute?
No.
No, nothing in the box, outside the box. But there will be 3 different boxes because each key is made up of different attributes. Okay, so look over here. This is the key. Of course, it functionally determines each one of these. Now, the question is A a subset of BC? No. Is D a subset of BC? No. Is E a subset of BC? No. Is F a subset of BC? Is F a subset of BC?
No.
No. None of these non-prime attributes are partially functionally dependent on the part of a key. They are dependent on the whole thing, not on B and C alone. Okay? Don't think like this. You are going to get all confused. Right here. This is C, D, and C, A. Okay? D is dependent on C, right? And C is dependent on C functionally determines A, right? That's what it is. All right. Now we have to look at again so that we can look at what is happening. Okay. All right. Let's look at this function dependencies by splitting them. AB determines F, you split right hand side. F determines E, C determines D, and C determines A. All right. Now notice that B and C are part of a key. A, D, E, F, they are non-prime attributes. So A depends only on what?
C.
A depends only on C. Right here. A depends only on
C.
C. And D depends only on
C.
C. What about E? Does E depend on any one of them? No, both of them. Does F depend on any one of them? No. So what we have seen here, that in this case, 2 non-prime attributes, A and B, are dependent only on a part of the key. Keys B, C, and they depend only on one attribute, C. They don't have to depend on one attribute. We could have a key made up of more than two attributes. They could depend upon the part of the key then. As a matter of fact, the problem number 4, where ABE was the key, that was the case. So this relation is also not in
Second norm form.
norm form. But I can give you another example here where I can make it not being in second norm form. Let me give you another example. Let's say we have R. Use a different color. Let's see here. Or maybe we should talk a little bit something and then we'll come back. I had given you a lot of examples last time. I can give you one of those, which I gave you. I gave you an example of CSZ. I said CS determines Z. Okay. Now, if we look at this example, just quickly, let's say this is it. Nothing else is given. Okay. Last time I had given you something else. Okay. CS determines Z. Therefore, what's the closure of CS? Closure of CS is? Come on, guys. What's the closure of CS? It is CS. And what else? Where is everybody?
I don't know, where are you pointing to, because we can't see the pointer. What example are you talking about?
At the bottom here.
Oh, okay.
Right here. So what is the closure of CS?
Z?
That's right.
C.
So we got closure of CS, CSZ. Okay. Now, does that tell us it is a super key? Yes. Now, what's the closure of C? The closure of C is what?
C.
C. And what's the closure of S?
S?
S. So it's also a minimal super key. Are there any other keys? No. This is the only key. Okay. So what are prime attributes? Prime is what? C
Yes.
and S. And non-prime?
Z?
Z. Okay. Non-prime is equal to Z. Okay. Now, this is the question. Okay. Here is not really any confusion. Z is dependent on what? C and S, which is actually a key. Is Z partially dependent on C or S, or is dependent on both of them?
On both of them.
Both of them.
So it is in the second
Therefore,
one.
Z being the non-prime is not partially dependent on any key. Therefore, this relation is in what?
In second normal form.
This relation is in second norm form. So I gave you different examples looking at different things. Okay. Now I'm going to give you an example of really something else right here. Here. And please look at my definition. Don't worry about the book definition, okay? Okay, now we want to talk about third normal form definition.
Professor, can you start a new page?
I need this page. I will turn it after this. Okay? I just need this, or I write it up here. You guys want to write it on the top? I got to write somewhere.
It's getting pretty cluttered.
I need this at the bottom piece, and then I can change it. Okay? Let me just write this down because you have it written down already. Okay, so you look at the left-hand side, any functional dependency, look at the left-hand side and right-hand side. Okay? So a relation to be in third norm form are to be in third normal form either the left-hand side is a super key. Super key. Don't look at the book telling you key. Super key. Any key is a super key. You know that, right? So if he tells you key, don't worry about it, because then that's the limited definition. It could be just a super key, not key. Either the left-hand side is super key, or where is or? Or right-hand side is prime. That's it. That's a foolproof definition. And do not try to use something else. You don't need the second normal form to know. Just go straight to third normal form. Okay, let's quickly see this and then I'll turn the page. Okay, let's look at this relation here, right here, right? Okay, and let's look at this function density. AB determines C. Now, AB is a super key. Yes, because AB, BC, and BD are all minimal super keys. AB is a super key. Is C prime? Everything here is prime. So let's look at this one. Is C a super key? No. Is D prime? Yes. The OR condition is satisfied. Is D a super key? No. Is A prime? Yes. Therefore, this relation R in example 1 is in third normal form. Not only in second normal form, is also in third normal form. Let me go over this again because this is very easy. Let's go over. So we are going to look at the left-hand side, and let me write down here, left-hand side, right-hand side. Left-hand side, and we are going to look at right-hand side of each functional dependency. Okay, so let's look at it. In this example, this is the function dependency. First of all, you have to find all the keys. Once you find all the keys, you will know whether something is a prime or whether something is a super key. Okay, all keys are super keys. Okay, now in this question, what were the primes? Everything was prime, A, B, C, D. And what was the non-prime? Nothing. So let's apply the definition here. Is AB a super key? Is AB a super key?
Yes.
Yes. So we don't need to worry about the right-hand side. Is C a super key?
No.
No. Worry about the right-hand side. Is that prime?
Yes.
How about this? Is D super key?
No.
No.
Is A prime?
Yes.
Yeah.
Yes. So the whole definition is satisfied. Let's look over here. You will find out same problem here. Okay. Okay. So we are going to cross this out. Okay. Okay. So we are going to take this one and number 2 here and number 3 here. And this is going to be number 4. My alarm is going. See, my alarm is keeping me on time. Okay. All right. So let's look at this question right here. The only key here is BC. We know already. BC is a minimal super key and a key. And everything else here non-prime. This is a prime. This is non-prime. Okay. So let's look at each one of them here. Is AB a super key?
No.
Is F prime?
No.
failed right here. This is not in third normal form. If one condition, one functional dependency fails, the relation failed already. Not to fail, it has to pass everything. Let's look over here. Is F super key?
No.
Is E attribute prime?
No.
Is C a super key? No. Is D prime?
No.
Is C a super key?
No.
What about A? Is A prime?
No.
Yes, I'm going to restate it. Right here, third normal form. When you look at a third normal form, you look at in a relations, every function dependency, you look at the left-hand side and the right-hand side. It's written right here. Definition of third normal form. Look at the left-hand side and the right-hand side of the functional dependency. For this to be in third normal form, relation R, okay, either the left-hand side, each left-hand side, not just one left-hand side, is a super key, or the right-hand side is a prime for each and every functional dependency. Let me write that down too, because you might misunderstand here. This is for all functional dependencies, not for one. Okay. Let's look at this one here, right here. This example 3. What is it? AB is a key, prime are AB, and non-primes are C and
D.
D. Look at that. B determines C. Is B a super key?
No.
Then C must be prime. Is C prime?
No.
That means this failed right here. This is not in third normal form. Of course, it's not even in second normal form. For a relation to be in third normal form, it must be in second normal form, by the way. Okay?
Okay.
But I am not going to allow you to use that, because I just want you to use the third normal form definition directly.
So do we check like backwards? Like do we do third and then C and then go back? Or what?
That's the way I'm going to give you questions.
Okay.
So that you don't have to use. I'm going to write there that you cannot use in using third normal form the second normal form definition, or in the book transitivity definition. None of that.
Okay,
Because
so-
you will fail in using that. Okay? This you will never fail.
Okay. All right. So if you're given a question right here, so we do the closure, find the keys, and whatever functional dependencies are given, we check the left-hand side and the right-hand side.
No. First you have to find out what are the primes and non-primes.
Sometimes. Okay.
And
Got
then simply check at each functional dependency whether the left-hand side is a super key. Then fine. If left-hand side is not a super key, then you have to check the right-hand side. Because the negative of either or is and in between. Not of that, not of that. I think you guys should know that. Here. Negative, not of A or B is equal to what? Is not of A and not of
B.
Today I don't have a time to show the logical diagram of this. I can show you afterwards. Okay, the truth table. Okay, the only one thing left here is what is Bose-Card normal form. Okay, I'm just going to tell you Bose-Card normal form is more strict than third normal form. In the third normal form, we allowed the left-hand side to be super key and the right-hand side to be prime. But In Bose normal form, every left-hand side must be a super key. That's it. Okay, so we will call that BC normal form, Bose chord normal form. Every left-hand side of each functional dependency must be That's it. We are going to show examples. So let's ask you this right here in this example. In this example, B, C, and B, D, well, B is not a super key and B is not a super key. So that's it, out. Okay? But in this example right here, what is the question here? Is this in Bose chord normal form? Well, in second normal form, third normal form is in Bose chord normal form. Well, each left-hand side must be a super key. But this is a super key. This is not. Neither is this. So this relation is not Bose chord normal form. So in the picture, the biggest diagram, you have every relation is in first normal form. Then you have second normal form. Then you got third normal form. Then you got inside Bose normal form. So this is 1. This is 2. This is 3. And this one inside is Bose chord. Now, when we design databases, relational databases, we would like the relation to be at least in third normal form. Okay? And many times we may get lucky the relation, if it's in third normal form, it will be in Bose chord normal form. Okay? But we have algorithms which can translate the relations into third normal form or Bose chord normal form. Or given the functional dependencies, we can actually construct them. Okay? So what's the definition of second normal form? There is no non-prime attribute which is partially dependent on any key. What's the definition of third normal form? We look at the left-hand side and right-hand side of each function dependency, and either the left-hand side is a super key or the right-hand side is prime for all function dependencies. Similarly, for the Bose chord normal form, the left-hand side of each function dependency must be a super key. Okay, now we'll give you some examples. Let's look at this one, CZ. Where is that CZ? Right here. This example. Okay, so we are given this relation RCZ, and CZ determines Z. Okay, we already know this relation is in second normal form because Z being the non-prime is dependent on the whole key. Is this in third normal form? Well, there's only one function dependency. Is the left-hand side super key?
Yes.
Yes. Now, there's only one left-hand side. It's a super key. So is it in Bose chord normal form?
Yes, it is.
It is in everything. First normal form, second normal form, third normal form. Sometimes you will find out that it is very sneaky to find out whether something is in second normal form or not. And you will make mistakes. So I will give you some example like that, which will trick you. Okay? So right now, take a picture of this, and then we can give more examples. Okay? So this sheet, you have a sheet on both of these things. So please remember to have the sheet. So I am going to give you another homework sheet. you are not going to be doing the homework sheet I gave you right now. There will be another one, and you will have to find the keys again by doing what I told you. Find all the super keys, and each super key you have to find the minimal super key. Once you do that, then you will use these definitions I gave you to tell me whether they are in third normal form or not. You can't just say relations in third normal form, first normal, this, that. If they are, you have to show me. If they are not, then you have to show me that they violate some condition, and you have to show me that condition. Don't tell me that, oh, it's not in second normal. Oh, it's not third normal. No, you will get nothing. You have to show me why. Okay, guys? So let me give you some more examples. So take this so that we can go over more examples.
Professor, while they're taking picture, can I ask you a quick question?
Please.
Yes, can we go back to original, like when you started doing the example 3 and you said that we have functional dependencies, B determines C and B determines D for example 3?
Oh, just 1 second. Which one? First one?
Example 3.
Oh, okay. Oh, yes. Go ahead. Let me get the arrow. Okay. Let's see. Okay, here. B
Right.
determines C and B determines D. Yes.
And you said that look at the right hand side, we have C and D. So what is missing? We're going to start with AB because that's missing here, right?
That's right.
So is there any scenario where like it happens that we have all of the attributes here and there's nothing missing? Or it never happens like
Oh, that's right here. Right here, for example. Oh, no. B is there.
yeah.
B is there. Okay. Now, right here, well, it depends also. You see, what happens is here, if you look at this example, this can actually fool you, right? So if you look at CS determines Z, right? What's missing on the right-hand side here? C and S.
Right.
So C and S will be part of a key.
Right. But this is like, what if it was that C was determining Z?
No. It's not a question of determining. It's just a question of when you, doesn't matter how many things are determining what. But if something doesn't appear on the right-hand side, it's like somebody's not selling something. Doesn't matter how much money you have.
Okay.
You can't buy it.
Oh.
Do you understand?
I don't know. From like what I was asking was that if everything is on the right hand side and if there's nothing missing, so where would we start from? Like in that case, what do we look at then?
Then you just have to look at the. You see right here, this example right here, where we said A determines B, B determines C, C determines D, D determines A. Remember that example?
Yeah.
Right? We had that. So now in that case, A determines B and B determines C, and C determines D, and then I gave you B determines A. Okay, now here, in this case, you see, let's just first apply what I said. Is there anything which is, okay, oh, the relation R is also made up of only A, B, C, D, right?
Yes.
R is only made up of
A, B, C, D.
A, B, C, D. Okay, guys, let's answer this question she's asking. Okay, So this is the relation, and all the attributes appear on the right. Right? So that tells us we could start with anything, we will get it. It doesn't mean how many we will have to start with, because this is too simple. But this could be quite complicated.
So in this case, we can start with anything. We could just start with A and just be like,
Yes, because we know that you can get anything from this side here, right? Anything. Because there's nothing which is not here.
okay, right. So
Now,
yeah,
in this little example, we knew CS is not here, therefore you have to start with CS. In this example, we knew A and B are not here, therefore you have to start with that.
right.
And in this example over here, we knew on the right-hand side, B is not there. But that doesn't mean if B is alone is the key. But we know that B will be part of the key. It won't be without it. You understand? So this is okay for a small problem, but a large problem, you have to use the computer. Because we could have thousands of function dependencies, 10,000, 100,000. Because what we do actually, maybe I should tell you guys the secret. There's another way of designing the databases. But that's also you have to be very, very smart, because you walk into the company, you study, you look at it, spend days, maybe a month, more, and then you write down what all their attributes are, and you write down all the function dependencies. That is what we call the meaning of the data. Once we have that, we got algorithms, which just do the job. We don't have to do anything. Okay?
Okay.
So the only thing I want to tell you is this. The functional dependencies of a relation, they code. They encode. I should use the word encode the semantics of the data of the enterprise. You want to write it down? The functional dependencies encode the semantics, data semantics of the enterprise. Semantics of data of an enterprise. This is very important. That's what they do. Okay? That's the meaning of the actually functional dependencies. This is the meaning of the functional dependencies. Meaning means semantics. Any semantics of the data, how it is being used in the company. That's what it means. The semantics of data of the company means how this data is being used in the company. And that is expressed in terms of functional dependencies. Do you guys understand what I'm saying?
Yes.
If you went to somebody in database and just said that, they will think, oh my God, this person may understand what they're saying. So remember this thing, okay? You can say this in an interview, that the meaning of the data of the enterprise is captured in the functional dependencies. Okay, now we have to do more examples. We got more time. So let me get an example, which may be little, let's see. Come on. Okay, I'll make it up. Okay, I always ask for this, okay? Because this is very, very important. All right, so let me tell you what the question is going to be so that you know what question. So did you take a picture? I'm going to erase it now. Guys, done?
Yes.
Okay, 1, 2, 3. So this will be the question. Okay, here is the question. You are given a relation R over these attributes B, C, D, E, F, G, and then you will be given functional dependencies. We will say with functional dependencies. Given this, with the following functional dependencies. Okay? Come on. Let me write it down, some functional dependencies, so that, okay. Let's say AB determines C and okay, AB determines C, C determines G, and I got here A, B, C, E, G. Oh, I don't have D here. Okay. Let me say, oh, I don't have F either. Okay. All right. I only have 6. All right. And let me see that the A, okay. Okay, this is what was given. And then the question will be, find, determine all keys. And then, of course, you have to give reasons. Reasons for your answer. No reason, 0. Second question. Is the relation, is R in third normal form? If so, why? Why? Anyway, whatever the reason you give, question is why. Okay. Then is the relation in R in Bose-Chord normal form? Again, why? Now, is in second normal form. Okay. And here you will be told not to use the definition of second normal form. Or the definition of third normal form from the book, which is the transitive key. Or book definition using I just write down book definition. Do not use same thing here. Okay. Same thing here. Do not use the definition of third normal form or second normal form. Okay, and then your question is why. Okay, let's do this now. Okay, the first question is we have to find all the keys. Okay, so let's look on the right hand side here right now. Okay, so we got A, B, C. We got A, B, C. We don't have
G. We don't have D, E, F.
or we don't have F anyway. So
Oh, we don't have so D, E.
A, B, C, C, G. We have A, B, C, G. We don't have D, E. Okay, so that means D is going to be part of a key. Okay, so let's just check closure of DE first. See if it works. Okay, it will be DE. If we go from this side, AB is a subset key? No. C is subset? No. Is D a subset? Yes. We'll get A, and that's it. When we go back, is AB a subset? No. CE a subset? No. D is a subset? Yes. We got already. A is a subset? Yes. We got to put B there. Wait a minute. Use a different color. We have to put B. Okay. Let's go back. Is AB is a subset of this? Yes. Therefore, we have to put C here. Okay. Is CE a subset? No. D is a subset? Yes. A is a subset? Yes. Now, second time, AB is a subset. So, got C. CE is a subset. We will get G. So, we will put G here. Okay. And then what? D is a subset. We got A is a subset. So, we got A, B, C, D, E, G. So, if we go again, we'll get the same thing. Now, what happened here? Since DE is a super key and a minimal super key, and therefore is going to be the only key, because if you add anything to do it, it will be only a super key. It cannot be a key. Does everybody understand that? DE doesn't appear here on this side. And if DE turns out to be a super key, then it's definitely going to be a minimal super key, and it's going to be the only key. So DE is the only key. Now, is this a relation in third normal form? Well, first let's find out which are the primes and non-primes. So the primes are, use a different color. Primes are, what are the primes? Prime attributes are
D and E.
D, E. Non-prime, everything else.
Yes.
Non-prime is going to be A,
B, C, and G.
B, C,
Yeah, and G.
and G. Okay, now we can easily look at it. Okay. Okay, let's try to find out if it's in third normal form. Is AB is a super key?
No.
No. Is C prime?
No.
It failed right here. Let's look at the next one. Is C a super key?
No.
Is G prime?
No.
We don't have to show too many, just one counterexample. Is D a super key? No. Is A prime? No.
No.
Is A a super key?
No.
No. Is B prime?
No.
No. So if I just look at one of these, AB is not a super key and the right hand side is not a prime. Therefore, it's not third normal form. Same
Oh.
thing with Gaussian normal form. Everything on the left hand side must be a super key. If one of them is not a super key, it's done. Take any example here and choose one of them as a counterexample and say that, hey, look at this, AB. A is not a super key, it's not a Gaussian normal form. Well, is it in second normal form? Well, let's see. So we have DE. Well, let's draw a picture. Let's draw a picture. So in this picture, we got two little boxes. Okay, so this is the key. D is in here and E is in here. Okay, and this is the key. This is the only key. So this is the only box we need to draw. Okay, now we need to draw A, B, C, G here. Okay, let me do that. I'm going to draw here A. I'm going to draw here B, C. You don't have to do this to answer the question. I'm just doing it so that you can have pictorial view of it, okay? Okay, so we got this in a box. Okay, so we know that these two together, they determine everything. Functionally determined. Okay, and we can show that by this arrow. That's what we use to show arrow. So we know that these two together do this. The question is, does any one of them separately do that? Well, let's look at it. Well, DE is a key and A is a non-prime attribute. And D determines alone A. Is that true or not?
Yes.
So we can show that in the picture is a black sheep. D alone determines, come on. D alone determines A. Right here, we got partial function dependency of a non-prime on a prime that's key. Prime will be part of a key, right?
Yes.
This imagery tells us this is not in
Second normal form.
and no other condition will give it, because look over here. C depends on A, B, that's no good. G depends upon, oh no, G, oh, we didn't even write G. What happened to G? We made a mistake here. This should be,
B, yeah, instead of G.
no, we should have A, B, C, G.
Yeah.
This should be G here. Okay, now what do we see? Well, AB, okay. A depends on what? D alone. B depends on A alone, but A is not part of the key. G depends on C and E, but they are not part of the, aha! I have to ask this question. Please, G depends on D and E. Yes? Is that right?
Yes.
Yes.
D and E depends on G. But the key is, what's the key?
DE.
DE.
No, key is DE.
Yeah.
Thank you. Now, okay, D determines G and D is the key, right? Now, the question I asked was,
If CE determines G.
okay, let me write that down here. C determines G. Here is the question, okay, which some people get confused, okay? Now, let's look at this carefully. G is functionally dependent on DE because DE functionally determine
G.
G. But G is also functionally dependent on CE. Is CE part of a key of DE? That's the question. Is CE a subset of DE? This is the
No.
question. And a lot of you will say yes. Is. Write this down question, okay? Is CE a subset of DE? Okay, we are done, guys. Anybody can leave. Remember to do the question the way I said it, okay? And they will be on the homework sheet. And there will be a 4-hour video on SQL. You will have to also do it over the weekend because now you're going to have a long weekend, okay?
And it's going to be very, very busy too.
Yeah, you have to be busy because the semester is ending and you have to do the project. I will also assign the project. All the people who are taking the course first time, they will do the project from the book, chapter 5, problem number 9. And I already gave you the modeling sheet. It's online and you better check it.
Professor,
Okay.
I have some questions about my grades. It looks like you actually missed.
Not
some
right now.
pages.
Now,
Right.
what do you mean? Looks like what?
It looks like you missed some pages. Like you didn't even.
Well,
grade
I
the
can only look at the pages which are there. There was, you had 1 through 7 pages. How many?
on the assignment number 7.
You have to wait 1 minute. You got to wait because
Yes,
this
sir.
is part of the, I told you guys that I am going to ask questions and answers part of this. Okay. Now, the most important question here, and a lot of you are going to make mistake. Okay. We have to ask the question, is CE a subset of DE? Obviously, CE is not a subset of DE. They have common E. That doesn't make it a subset. The whole thing has to be part of this. So you may get a question just like this and then say, oh, yes, it is. And it's not in second norm form just because of that. Because if we don't have the other part here, let's say we don't have this part, we don't have this. And then you may say, oh, it is. Okay? It is not. Remember this question. Now leave this in here for your example. It is not. This is a very important question because something like maybe in your quiz or homework or on the exam. Okay? Now, as I said before, you have to justify all your answers. Okay. Now, the first thing here is anybody has any question, I will answer that. And then I will answer anything else anybody has. Because to answer that question, what I saw on your submission I will have to go back to the grade sheet and look at your questions. Okay? Otherwise, you cannot answer it. So anybody else has any question?
I have another question about homework, but I'll wait until after.
Yeah, who's this?
Robert.
Okay, Robert. I can only answer that question by going back to the homework and looking at if you have any question, okay?
Okay. Can I just discuss it with you real quick?
Not right now. Okay? Because I can't go back and look at it.
Why not?
Say it again?
Why can't you go back?
I cannot go back right now because I gave this time for quiz, question and answers.
Can I wait till after?
Yes,
Okay, cool.
I promise that I will give time for question and answer. If nobody has any questions and answers, I will close this session. Okay? So check the, Sarah, you have a question?
Yes, I do, about the example one that was on the previous page.
Okay, go ahead.
I just wanted to ask that once you said that everything is on the right hand side and we could start
Let
off
me
with
see here. Well, first of all, what was the example? A, B, C, D, right? And what about the functional dependencies? A, B, determines C. That's the one.
Yes.
And C determines, what did I say? B determines, no. What was that? Just a second. I think I might have it here. Oh, C determines D and D determines A, right? Okay. Now let me get me a pointer. Okay. So what I said here was, if you have not too many functional dependency, you can try to examine the right-hand side and see which of the attributes are not on the right-hand side. And in this case, B was not there. Is that the question?
Yes, B was not there, and so like I know we start off with B, right?
Yeah.
Okay. Then I just
But the closure of B really doesn't give you anything. It just gives you B.
right. Okay, yeah, that's what I wanted to, like, if you could go over it very quickly. I just wanted to find out the point where you get to finding the keys.
Okay. So we know that B has to be part, right?
Yes.
And then we have all these other attributes, A, C, and D.
Yes.
So we can try them one by one. So let's say we try BA. So let's closure the BA, right?
Okay.
So that will be BA, right? And we got C, and we got D. Okay, that's good. So let's try something else. Let's try combining B with the C.
Okay.
And it turns out we get B, C, and then from C we can get D, and from D we can get A. Oh, that works too. So let's try BD. That's the only thing left.
Right.
Now find the BD closure. And we say, okay, BD. And from BD, we can get A. And then from AB, we can get C. So the only thing we have to establish here is that what is the closure of B, which we already know was only B, right? And the closure of A was only
A.
A, and the closure of
C was D.
C was equal to CD, right? Right? And
Yes.
A. And A too. Because you get from C, you get D, then when you come back, you also get A. So the closure of, if you look at AB, it is the minimal super key because B is not a super key, A is not a super key. We already established here B is not a super key. And now we establish C is not a super key. Here we establish B is not a super key, but we have to look at D. So let's look at D. The closure of D is equal to D, and from D we can get A, right? And that is it. So the only thing we have to show here, Sarah, is that make sure that the parts of this are not super key. So if we happen to have a bigger attributes, A, B, C as the key, then you will have to try A, B, you will have to try A, C, you will have to try B, C, and so on. Then you will have to try again, A alone. And
So whenever we have everything that on the right-hand side, so we take it apart, the left-hand side, and see individually if it covers everything. If not, then whatever is together is the super key.
yeah. Well,
Wasn't it that the subset of the key, if they were not super keys, then it's a key?
Say that again.
So the subsets of a key, if you take them apart and they're
That's
not
right.
super
If they're
keys,
not super
they're not
keys,
key.
then they are not going to be key because we have to have minimal super keys. You are right. That's right, Robert.
Okay.
All right.
All right, got it. Thank you so much, Professor, and so much, Robert.
You're very welcome. Yeah, try to follow it step by step and reason it out, because otherwise you miss the steps, then you haven't proven it.
Okay. All right. Okay, I'll just keep practicing, and if I get stuck, then I'll email you.
All right. Okay, Scott, let's see. Who else has a, Robert, you just hold on.
All right. Thank you. Goodbye,
You're
Professor.
welcome. Anybody else has a question?